In lesson 8.4, we're going to talk about finding and using a special matrix called the inverse matrix. Before we talk about the inverse, we need to have an understanding of a special matrix called the identity matrix. And the identity matrix is the second matrix that's listed here in the 2 by 2 form. It's 1, 0, 0, 1. And let's see what happens if we were to multiply any matrix in front of the identity matrix. So although there are some numbers filled in here, know that that's just representing any matrix in general. So if we think about the process for multiplying a matrix by a matrix that we talked about in our previous lesson, we're going to think about doing a row by column multiplication. So we'll do 5 times 1 plus 7 times 0. So the elements in the first row are multiplying by the elements in the first column. All right, let's look at the first row and the second column. So that's going to be 5 times 0 plus 7 times 1. All right, multiplying to get the elements in the bottom row. Let's do the bottom row by the first column. So that's going to give us 2 times 1 plus 3 times 0. And then finally, we'll do the bottom row of the first matrix with the second column of the second matrix. So that's going to be 2 times 0 plus 3 times 1. So if we go ahead and simplify that down, for the first element up here in the upper left, we have 5 plus 0, which is just 5. The second one, we have 0 plus 7, giving us just 7. Next, we have 2 plus 0, which is 2. And then we have 0 plus 3, which is 3. So notice how the elements stay the same. They don't change from the original matrix that we started with. So if we multiply by the identity matrix, it's going to be the same thing. It's sort of like in the real number system, multiplying by the identity, which is 1, it's going to cause whatever we multiply by 1 to stay the same. Anything times 1 is equal to itself. In the world of matrices, anything times the identity matrix is equal to itself. So now let's talk a little bit about the inverse matrix. First off, using some notation, here you'll notice that we're using the kind of the inverse symbol, the little -1 up here that kind of looks like an exponent. It's not an exponent, but that's the symbol that we use when we're describing the inverse of something. A few things to know about the inverse matrix is that we can only find the inverse of a square matrix. And so a square matrix is when the number of rows is equal to the number of columns. So a 2 by 2 matrix, a 3 by 3, a 4 by 4, we would never find the inverse for something that was a different size, different number of rows as columns. The other interesting thing to know is that not every square matrix has an inverse, and we'll talk a little bit later about what that situation would be. And the special property is that any matrix, we'll call it matrix A, multiplied by its inverse is going to equal the identity matrix. And the identity matrix is going to have a special letter that we use to represent it. We'll always use a capital letter I to represent the identity matrix, the 1, 0, 0, 1. And what's really interesting is that we can change the order. We could do the inverse matrix first in front of our regular matrix, and it will still equal the identity matrix. If you recall, in the last lesson, I mentioned that normally we cannot change the order when we are multiplying a matrix by a matrix. Usually, matrix A times matrix B is not equal to matrix B times matrix A. This is that special case where we can change the order around and we get the same answer because either way it's going to equal the identity. Okay, so using this information, let's show that two matrices are inverses of each other. We are going to show that matrix B is the multiplicative inverse of matrix A. And the way we'll do that is by multiplying A times B and then we will multiply B times A, and both times we're going to show that it's equal to the identity matrix. So let's find A times B first. I'm just going to go ahead and recopy A and B. Side by side, we'll put matrix A in front. And thinking about the row by column multiplication, we'll be looking at the first row with the first column. So we're going to do 2 times 1 plus 1 times -1. All right, next we'll look at the first row with the second column over here. So that'll be 2 times -1 plus 1 times 2. On the bottom row, we're going to have 1 times 1 plus 1 times -1. And over here, we've got 1 times -1 plus 1 times 2. So let's see how this simplifies down. Up here in the upper left, we get 2 plus -1, which is 1. Then we have -2 plus 2, which is 0. 1 plus -1 is 0. And -1 plus 2 is 1. So sure enough, the first round, doing A times B, is equal to the identity matrix, 1, 0, 0, 1. Okay, let's check the other direction of the multiplication by finding B times A. So I'm going to rewrite this, but we're just going to change the order around, putting matrix B in front. All right, let's do our row by column multiplication. So we've got 1 times 2 plus -1 times 1. Over here we have 1 times 1 plus -1 times 1. On the bottom row we've got -1 times 2 plus 2 times 1. -1 times 1 plus 2 times 1. All right, so simplifying this down, we've got 2 plus -1, that's 1. 1 plus -1 is 0. -2 plus 2 is 0. And -1 plus 2 is 1. So we end up with the identity matrix again. So notice this is that special case where we can change the order. A times B is B times A if and only if B is the inverse of A or if A is the inverse of B. Okay, so we've seen how we could verify to see if something is the inverse of another matrix. Let's next talk about how we can actually find the inverse. So let's say for a new matrix A, we'll call this 5, 7, 2, 3. Let's say that A inverse, what we're trying to figure out, let's use variables to represent the elements, W, X, Y, and Z. So we know that a matrix multiplied by its inverse is supposed to equal the identity matrix. So let's show if we do matrix A multiplied by A inverse, which we're calling that W, X, Y, Z, we're going to show that that's equal to 1, 0, 0, 1, which is the identity matrix. So over here on the left side, we could think about that row by column multiplication to simplify this down. So we could do the first row by the first column. That's going to be 5 times W plus 7 times Y. Then we'll do the first row with the second column, 5 times X plus 7 times Z. For the bottom row, we'll get 2 times W plus 3 times Y. And then we have 2 times X plus 3 times Z. So let's go ahead and put that equal to the identity. Now we have a 2 by 2 matrix set equal to another 2 by 2 matrix. If two matrices are set equal to one another, that means that the elements that are in corresponding positions must be the same. And so that means that 5W plus 7Y must be equal to 1. 5X plus 7Z must be 0. 2W plus 3Y must also equal 0. And 2X plus 3Z must be equal to 1. So let's actually write out these statements. And what we've actually created here are two systems of equations, which we could solve for each one of the variables that we're looking for. So notice how the first two equations over here are for the variables y and w. Let's think about solving this one using elimination. Let's multiply everything in this top equation by +2. And let's multiply everything in the bottom equation by -5. All right, when we go ahead and add these together, we end up getting that -y is equal to 2. So y would be -2. Let's go ahead and put a box around that. And we'll go ahead and plug that back in to one of those original equations to solve for w. I'm just going to plug it back into this one. And we end up getting that w is equal to 3. All right, let's go back over to this one and notice how these two equations are both using x and z. So we can solve these together. Let's do a similar process to think about eliminating. Let's multiply the top equation by 2. And let's multiply everything in the bottom equation by -5. All right, so we end up getting that -z is -5. So +z would be +5. We'll go ahead and plug that back in to one of our original equations. Okay, so we end up getting that x is equal to -7. All right, so we have successfully solved for the 4 variables that we were looking for. So originally we said that A inverse was equal to the matrix filled with W, X, Y, Z. And now we found out that W is 3, X is -7, Y was -2, and Z was 5. So this would be the inverse of that matrix A. Now that was kind of a lot of work to get the inverse. The good news is that there is an easier and faster way. If we're wanting to find the inverse of a 2x2 matrix, so let's look at this example. Let's say any matrix, we'll just call it A, B, C, D. This little formula for getting the inverse, we're going to do 1 over A times D minus B times C. So what we're doing here is we're kind of multiplying the two elements that are diagonal, so A times D minus B times C, and we're going to multiply that out in front of this version of the original matrix where the A and the D have switched places, and the B and the C now have a negative sign in front. So this is a little formula that we could memorize. An easy way to remember what's going on here, A and D switch places, and with the B and the C, we're going to negate those, which is another way of saying that we're going to make them negative. Okay, this part right here, let me highlight this with a different color here. So this part here that's highlighted in pink, just the part that's A times D minus B times C. This has a special name. It's called the determinant. And so what we're really doing is 1 over the determinant multiplied by this switching places and making the B and the C negative matrix. So if the determinant of our matrix is 0, that means that we would be doing 1 divided by 0 out in front, which is undefined. And that's the case where there is no inverse. Remember at the start we said we can only find the inverse of a square matrix But not every square matrix has an inverse, because if we end up dividing by 0, it simply will not exist. Now, before we move on, so there's a couple of examples that I see here, but I want to actually show you how this formula will work with the previous problem, because I want to convince you that this formula works. So if we go back to what we did over here, let's just maybe write off to the side. A quicker way to get the inverse of this is to do 1 over a times d, so that's going to be 5 times 3, minus b times c, so that'll be 2 times 7, and we're going to put that in front of the matrix, so the a and the d are going to switch places. So in this case, that's going to be the 5 and the 3. They're going to switch. And then the other two, we're going to put a negative in front. So we have -7 and -2. So let's see what happens when we simplify this down. Looking at the fraction part in front, we have 1 over 15 minus 14. That worked out really well, because 15 minus 14 is 1. 1 over 1 is just equal to 1. They won't always work out this nicely, but this one did. And so 1 times anything, of course, that will just remain the same. So it's saying that the inverse is 3, -7, -2, 5. Let's compare that with the inverse that we got down here. Look, it's the same. 3, -7, -2, 5. Okay, so I want to convince you that that process works. So let's practice the method again, finding the inverse for these two. I want you to actually pause the video, try this on your own, and then restart the video when you're ready. All right, so if you're back on the video, hopefully you've had a chance to already try these. So let's go ahead, and I'm going to put the steps out here so you have a chance to check your work. For this first one, we're going to have 1 over 2 times 7 minus 4 times 3. And then this matrix here, we're going to switch places, the 7 and the 2. And the 3 and the 4 are going to become negative. So the fraction part in front, we end up getting 1 over 14 minus 12. 14 minus 12 is 2. So we're going to end up with a fraction of 1/2 out in front. And then we're going to want to distribute the 1/2 into this. And so that's going to give us a final inverse answer of 7/2, -3/2. On the bottom row, 1/2 times -4 is -2. 1/2 times 2 is 1. So that'll be the inverse for that first one. All right, checking our work for the second one, we're going to get 1 over -11 times 2 minus 5 times -4. And that'll be in front of, we're going to switch places, the 2 and the -11. And then the 5 and the -4, we're going to think about putting a negative in front. So that's going to turn it into a -5. The negative in front of the -4 is going to make it a +4. So let's look at what's happening here. So on our denominator, we get -22 minus -20. So we know that's going to be the same thing as plus +20. And so -22 plus 20 is -2. So altogether, this will be the fraction -1/2. We'll go ahead and bring this down, and we'll multiply the -1/2 through to the inside elements. So that's going to end up being -1, +5/2, -2, and +11/2. So that will be the inverse for the second one. Okay, so this is actually how far we're going to get today. We will finish this in the next lesson. We will talk about how we're actually going to use the inverse matrix to help us solve a system of equations.